Okay, hello everyone. So we will start with the first chapter of mobile communication course, and this first chapter will focus on an introduction to cellular system. Okay. So typically at this introduction, uh, we will see together uh, what are the possible possible standardization body and how the standardization process is done. Then we will check together the cellular concept, okay, how this cellular system is working and based on this cell concept. And we will see the hexagonal geometry and the co-channel ratio interference and what are the different radio propagation environment. After that, we will see together the mobile network architecture evolution. And remember that in this course, we will start by, after doing that, we will continue investigating the second generation cellular system, which is the GSM. We will investigate with GSM. You can check the syllabus of this course. We will investigate the radio interface in details to understand how this radio interface is working, and after that the system, the planning of the system, and we will do some dimensioning. Okay, and after that we move to the other generation. We move to the third generation, which is UMTS, and we check the radio interface also, which is based on CDMA, and we see what's the difference at the architecture level in comparison to GSM. After that, we go to the fourth generation and we investigate the radio interface, which is based on OFDM. Okay, so we will see, we already presented OFDM last year in the digital communication course. So we will see how this radio interface is used in fourth generation, and we see what are the major, let's say, modification at the architecture level. And we will also investigate the MIMO technology, okay, in order to see how MIMO is also used in the new cellular generation. And we will see together an introduction to 5G, okay, mainly the different adopted, let's say, services and application. Okay, so this is typically will be the content of this course, and I hope that you will be able to follow all details. Okay, so typically, as an introduction, we know that the first generation of the uh, cellular system was a simple, let's say, analog system. Okay, it was an analog, and it was not used at high level. Okay, so typically when we talk about cellular system, we start really with the second generation here. It was at the beginning of the 1990, and it was the GSM standard, the standard that was, let's say, used at large scale, which is GSM standard. And this was a big success, okay, because it was a kind of extension of the fixed telephony network to be able to move and to communicate with other people. And after that, due to the big, let's say, expansion and the big use of GSM, they tried to add additional services like value-added services here, and after that to add internet, which is data, using GPRS, and to improve also the bit rate. They also propose GSM with Edge. Now at your telephone, when you have the sign E for data, it's Edge technology. Okay, GPRS and Edge technology are the two technology proposed in order to support data service over GSM. Then we moved to around, let's say, 2000 with the third generation. And here in the third generation, we talk about UMTS, okay? With Edge and with GPRS, the data bitrate was in theory up to 171 kilobit per second, but in practice it was, let's say, close to the modem bitrate at that time, which is typically around 60 kilobit per second or 56 kilobit per second. For UMTS, they 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 estimate to have, let's say, a bit rate around 2 megabit per second at the cell level. This was the objective in 2000, okay? But when they started this technology, they find that we need more bandwidth, and because they proposed a lot of services, we will see this together, and they move also to add additional enhancement, which was HSDPA and then HSUPA, which is high speed downlink packet access. And that's what when in your phone, this technology, when it's H, you find the letter H when this technology is used in your phone. After that, they move to the fourth generation and then to the fifth generation and fifth generation, where in fourth generation we reach a bit rate of 100 megabit per second. Okay, it was around 2010, something like this. And now with five generation, we are able also to have more bandwidth, and there is a lot of research work now on sixth generation. Okay, so this is typically the the evolution of the mobile network, okay, over the time. And if we can see this figure here, we can see the evolution also in comparison with mobility and bitrate, and we can see that if we want a high mobility in all technology, so in this case the bit rate will decrease, but if we are at low mobility, we can have high bit rate. Let's take, for example, the case of fourth generation. For example, we at low mobility we can reach, let's say, 100 megabit per second. But if we are at low mobility with this technology, we could be, for example, at 10 megabit per second or at 1 megabit per second, according to the possibility to have these services at such at the velocity or at the movement that we are doing. Okay, so this is the brief introduction about the evolution of the mobile network, and we will see them in details in the future chapters. So let's see together what are the standardization body, because all communication system are standardized, and we have different standardized bodies that specify the technical aspect related to the this such technology. So the first one is the ITU. The ITU is the International Telecommunication Unit. It's really تابع على الأمم المتحدة هيدي. So the headquarters is in Geneva, and it's as we said, it's an international organization within the United Nations. Typically, the government and the private sector coordinate the global telecom network are a part of this organization, and there is a sector ITUT, which T here stands for telecommunications. It's a sector to produce or to focus on standards covering telecommunication. Okay. The other standardization body is the ETSI, which is the European Telecommunication Standard Institute. This really is well known because it was responsible for the development of the GSM specification, and he also played an important role in the third generation system and so on. Another standardization body, which is the Australian one, is the Alliance of Radio Industry and Business. It's responsible of the uh, 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 standardization at Australian region. Other, the ANSI, which is the American National Standard Institute. It's a well-known institute. It's provide a forum of more than 270 ANSI accredited standard. It's represent a lot of organization in private and public sector at USA, and it's responsible for a lot of, let's say, the standard development for the American network. Okay, those are standardization body, and there is also another one which is the 3GPP, the third generation partnership project. In fact, after developing the GSM, this body was created to maintain the overall control of the specification design for the third generation. So it was around just before 2000, and the objective was to have, let's say, a different body inside. So within the 3GPP, we have ETSI, we have ANSI, we have a lot of organization, we have a lot of, let's say, mobile network operators and mobile network constructor like Nokia, Ericsson, Orange, Vodafone, and so on. And the objective was to be them together in order to work for a complete set of specification that will maintain the global nature of 3GPP, and also they continue with the other generation. So those are the typical standardization body. Let's see now what's the standardization process. So how the standards are elaborated. So typically when we are doing or we are working in standards, it's not really a one-time job. So it's a job that involves a lot of partner or organization, and it's ongoing process because we have different establishment. So we have to the first phase, which is the requirement, and here uh, it's we should decide what's to be achieved here, what's to be achieved by the standard. So what are the requirements? Why we need this standard and what should be achieved? And after that, we we move to the architecture, and here in the architecture we should define, let's say, the main uh, blocks, and let's say the interfaces we are using, and it's a kind of big vision about the system. Okay, and after that, we should go into details. And here we should take, as we said, each block and each interface, and we should specify them in details. After doing that, we move to the phase 4, which here is the testing and verification. And here we should test the interface specification that we specify to see if they will work in the real system, okay, in the equipment. So as we said, so when we define the requirement and we are developing architecture, it's based on the result to have some, let's say, modification or some update. At each level, we are able to update, to go backward, and to see after making this phase that we should update something in the previous phase. And also for testing and validation, it's possible to update at the other phases. So that's why we say that those phases are overlapping and iterative. Okay, because it's a continuous process. Okay, so for example, you can, as I said, you can update, you can add more requirement, you can change, and so on. Even sometime, if you added some, let's say, a big requirement or something that is not easy to be done in real life, you can remove, for example, you can remove some, let's say, requirement, or you can drop it and so on. So this is typically the standardization process. And you know, the result of 3GPP result are as the release. So you will find standards as release 10, release 11, release 12, and so on. If you want to see standard provided by, for example, other institution, for ITU, you have some numbers for each standards according to the context. Okay, so those are typically result. Remember that when we when we presented some in the course of security, we said, for example, that, or in the network, the standards here provided for the internet, IETF, it's an Internet Engineering Task Force, and the standard provides are request for comment. So you will find TCP, UDP, all of them with RFC with a certain number. So those are considered as standard for those protocol. If you want other organization standard, for example, IEEE, it's Institute of Electrical and Electronic Engineering, and the standard provided by this institution will have some number like IEEE 802.11, which is the Wi-Fi standard and something like this. Okay. So now, if we want to see here, it's the all IEEE standards here, and or here are the European standards, and here are the North American standards. Okay, and I want just to give you a brief description why we put IEEE here, because the wireless system, the mobile network, are coming from the telephony background. يعني الأوبريتور اللي كان عندهم fixed telephony, they work in order to move to have a kind of voice call, but with mobility. And after that, with the next, with GPRS, they started to add data, which is internet service. And now with LTE and all of them, we have both voice and data and internet services, and we have them with mobility. Okay? We have them with mobility. So we uh, we with IEEE, as we said, uh, they proposed they are working with internet, and the first standard was to have Wi-Fi. With Wi-Fi, we are able to have internet service, but with low mobility. You know, with Wi-Fi, the range is, let's say, less than 1 kilometer, or some, let's say, some hundreds. And they want to have, let's say, high mobility, and also they want to propose, in addition to the internet service, that is the service they want to propose the voice service. So that's why we moved to other technologies, which is, for example, 802.16, which is WiMAX. And here we propose to have, in addition, some kind of different cells, and they propose services like voice over IP. So we are able to provide internet and voice even in the internet based approach, and we are able also to have voice and internet services in all telephony background based systems. Okay. Now we consider that they are a complementary system. Some of them consider that they are a concurrent system. في منافسة بيناتهم أو بيكملوا بعضهم. This is a discussion. Okay, you will find it in a lot of let's say a paper or a lot of presentation, but typically each of them عنده الكاركترستيك الخاصة فيه. Okay. So here if we want to go to 3GPP to see the different standard, here we see the evolution, okay, from the release. We started with 3GPP to provide the third generation, and it was UMTS. It was the release 99 at this year, and after that, at each time we have an update in this standard. We provide this as a release 5, and we have a major modification. For example, in release 5, we added the HSDPA to increase the bit rate. In release 6, we added the HSUPA and so on. In release 7, we added MIMO. In release 8 here, we start working with LTE and so on. And if we continue to release 10, 11, 12, we have LTE advanced, and here starting from 20, we talk about 5G, and we continue. Now we are working on 6G. Okay, and when the release it's okay, it will be published as the release with the according with the number. So this is to let you understand how the specification is done, in the cellular system. So after having this brief overview, let's start together to understand the cellular concept. So why we adopt a cell? So because we knew we need an efficient use of the available channel, and we should use low power transmitter if you want to apply, let's say, at one cell at the country. So here we need a lot of radio resources, and we need also high power in order to reach all terminals. So that's why cellular systems are designed to operate with a group of lower power radios spread out over the geographical area. And in this case, this was the cellular concept that we should, the area served by each group of, radios is called a cell, and each cell has an appropriate number of low power radio to communicate. And the exact coverage of the cell depend on the area and the environment. And this, what we will continue, it's an approximation when we take that the coverage is a kind of regular polygon, so it's kind of approximation. And the idea here is that we have what we call a cellular concept. So we take a certain number of radio resources, okay, and we use this concept. So we have, let's say, the cluster size. The cluster size is considered as the area where we are using the radio resource. So if we have, for example, the cluster size equal n, this means that we have n cells. And here, for example, those are n cells. 7, here we have n equals 7. So we have 7 cells, and in this case, all radio resources are used within those n cells, and after that we can reuse the radio frequencies in other 7 cells. That's why if I have, for example, let's say 100 frequencies, I will use them over those 7 cells, and after that I can reuse them on the other 7 cells. Okay, so that's why when we talk about cluster, بالكلاستر بنستعمل cells مرة واحدة بالكلاستر وبعدين فينا نستعملها in other clusters. Okay, that's why it's very important to understand the cellular concept. Okay, and if we have, for example, a cluster is equal to 3, in this case we are using 3 cells cluster, and the radio resources, the frequencies are used within 3 cell, and after that we can use them with another 3 cells and so on. Okay, so within a cluster the frequency is used once. This is the typical concept of the cellular. Okay, so the idea here to find the distance between two center of the hexagonal cell. Why? Because we said that here I'm using cell, and this is the same cell in the other cluster. So here we can use the same frequencies in one here and in one here. So that's why if we are using the same frequencies, okay, we should design in a way that we avoid the interference between those two frequencies. So that's why we should find what the distance between the two, what we call them interfering cell. Okay, so that's why we put here, we are using the same frequencies on those one, okay, because they are in a different cluster, so we can use the same frequencies. And in this case, we should find what's the distance in order to avoid the interference between them. Okay, and typically, if we want to adopt the cluster size n, typically the cluster size n is given as follows, which is I square plus g square plus ij, where I and j, we want to take this ax and it will give me two steps and one step. So I, it will be one direction and j the other direction. Okay, so typically if I want to take them 7, so this means that we have two in this side and one in the other side. Okay, you want to see this. So we have two step here from 1 to here, 1, 2, which is I equal 2, and then we have one step in this direction, j equal 1, and this will give us the number of 7. Here it's two steps, I equal 2 and j equal 1. Okay. So here, if you want to calculate the distance between two centers, it's a geometric calculation because here it's an approximation, and if we have R is the center to vertex distance, and we want to find D, which is the distance from the center to center from two cells, so we can make some geographical, we can some geometry formulation, and we find that the relation is that the distance is equal to r radical 3. Okay, this is the distance between two adjacent hexagonal cells. So the idea here is that if I have this cluster, okay, we can also find, based on the geometry formulation, uh, a relation between the cluster size and the distance. So this is the distance between the two cells working on the same frequencies, and this is the radius of the cell, and we have n, which is the number of cluster size. We make a geometry calculation, and we found that the relation is d over r equal radical 3n. Okay, and we define q, what we call the ratio between the distance between the two adjacent cell using the same frequency over r, which is the same, the radius of the cell. So now we have the relation between the reuse factor and the cluster size or reuse factor, the distance between two adjacent cells using the two cells using the same frequencies, and are the radius of the cell, and this will allow us to design a very good cellular system. And to design this, we have to take into consideration the signal to noise interference. So let's say if we are, if though in those frequencies, in those cells, we have the same frequencies, so this means that we have a kind of interference between them. So the objective is to design them in a way to have the minimum interference, or the interference that will not impact the service. So in this case, we will define Ik to be the interference due to the Chi-M interference, and Ni to be the number of interfering cells. Remember that here we have the first ring, we have the second ring, we have the third ring, which are using the same frequencies. So typically in cellular system, we consider that the interference coming from the first ring is the strong one, and the other one could be, let's say, removed or negligible. Okay, so that's why if we are working in the complete case, in this case, the signal to interference ratio at this level, we are here. So we have a useful signal from the base station, and we have the other signals coming from the other cell. So we have the useful signal, which is S, over the interference coming from all other cells. If we want only to take, in our case, the first ring, so that's why we have the summation from k equal 1 to 6 to the interference coming from the neighboring cell. And in this case we can make, because we have the same propagation loss and so on, we can find this relation according to the uh, nature of the environment. You know that the signal, we already did this in digital communication, and it's the propagation is typically proportion to 1 over d to power n, where d is the distance and n is the path loss of the environment, is the according to the environment, n equal to for free space. Okay. And if we want to take the worst case scenario here, we apply the worst case scenario, which means that the user is close to the border. In this case, we can make the calculation and find that the signal to interference ratio is like this. So when we have a formula like this, we can, for a given service, if we should respect a certain signal to interference ratio for a given radius of the cell, we are able to find the distance, okay, or to define the cluster size. So that's why it's very important to know this cellular concept. Based on ASIR, we can find the Q, and we can find the cluster size, for example, or whatever. And if we want to work with three sectorial, here those cells are omnidirectional antenna. If we want to work with three sectorial, in three sectorial we have, uh, here it will be a cell, here it will be a cell, and here will be a cell, and we have one site for them. We can use in this case the same idea, but in this case the cluster will take into consideration the interfering sector in the same way. Okay, and here just some recommendation regarding the adjacent channel interference. If we are at the same, if we are at the same cell, okay, and we have a spectre, we have F1, F2, F3, due to the equipment we are using, it's not perfect. So sometimes we could have some Doppler or some shift in the frequency. So that's why it's very important to respect the